Hello there, and welcome. Tonight we drift among the stars into the vast cosmic ocean that stretches above us every clear evening. We'll explore the fascinating secrets of these distant suns, the gentle mysteries that have captivated humanity since we first looked up at the night sky. Some of what we'll discover will be soothing, like the way starlight carries ancient stories across impossible distances. Others will be breathtaking, like how the very atoms in your body were forged in the hearts of dying stars billions of years ago. But each revelation will open a window into the cosmos, stranger, more beautiful and more connected to us than we often realize. This evening, we'll wander through stellar nurseries where new stars are born, trace the lives of these cosmic giants, and uncover the quiet ways they shape everything around them. You might find yourself drifting towards sleep as we journey through space and time, or simply letting these celestial wonders flow peacefully through your mind. If you enjoy these nighttime explorations of the universe, feel free to like and subscribe and share your thoughts in the comments below. But for now, all you need to do is get comfortable, let your breathing slow, your thoughts soften, and allow the wonder of the stars to wash gently over you. Let's begin our cosmic journey. Stars of dust and gas that drift through space like are born in clouds' cosmic fog. These stellar nurseries, called nebulae, stretch across light years of space, filled with the raw materials needed to create new suns. Within these clouds, gravity works slowly and patiently, pulling particles together grain by grain. As matter accumulates, it begins to heat up from its own gravitational compression. What starts as a cold, dark region gradually becomes warmer and denser, eventually reaching temperatures so extreme that nuclear fusion ignites. In that moment, a star is born, beginning a journey that may last billions of years. The Eagle Nebula, one of the most famous star-forming regions, creates new stars in towering pillars of gas and dust. These cosmic sculptures, stretching several light years in height, are slowly being carved away by the radiation from nearby young stars. As the intense stellar winds strip away layers of material, they reveal the baby stars hiding within, like cosmic archaeologists uncovering ancient treasures. Each pillar contains enough material to create dozens or even hundreds of new stars, ensuring that the galaxy continues its slow dance of stellar birth and death. Our own sun formed this way roughly 4.5 billion years ago, condensing from a cloud of gas and dust left behind by earlier generations of stars. The leftover material from our sun's formation eventually clumped together to create the planets, asteroids, and comets that make up our solar system. In a very real sense, we are all children of that ancient stellar nursery, made from elements that were scattered into space by stars that lived and died long before our solar system existed. Stars come in an extraordinary range of sizes, from tiny red dwarfs barely larger than Jupiter to massive blue giants hundreds of times wider than our sun. The smallest stars, called brown dwarfs, never quite manage to ignite nuclear fusion in their cores. They left low dimly with overheat from cooling over their formation, slowly billions of years like cosmic embers. These failed stars are surprisingly common, possibly outnumbering normal stars in our galaxy, yet they remain largely invisible to us because of their faint light. On the other end of the scale, the largest known star, Scuti, is so enormous that if it replaced our sun, its surface would extend beyond the orbit of Jupiter. A passenger jet flying at typical cruising speed would take over 1,000 years to circle this stellar giant just once. These massive stars burn through their fuel at incredible rates, shining with the brightness of millions of suns, but living relatively short lives of only a few million years. They are the sports cars of the stellar world, spectacular but brief. The color of a star tells us about its temperature and age. The hottest stars shine blue-white, with surface temperatures reaching 50,000 degrees Celsius or more. Cooler stars glow yellow like our sun, while the coolest stars appear red, with surface temperatures barely hotter than a campfire. Paradoxically, the most massive stars are often the hottest and bluest, burning their nuclear fuel so rapidly that they race through their entire life cycles in just a few million years. Meanwhile, the smallest red dwarf stars burn so slowly and efficiently that they may continue shining for trillions of years, long after our sun has died. Stars spend most of their lives in a delicate balance between two opposing forces. Gravity constantly tries to crush the star inward, while the outward pressure from nuclear fusion in the core pushes back with equal strength. This cosmic tug-of-war creates a stable period called the main sequence, during which a star shines steadily for most of its existence. Our sun is currently in this peaceful phase, having spent the last 4.5 billion years maintaining this perfect equilibrium. It has enough hydrogen fuel remaining to continue this stellar dance for another 5 billion years. Fusion happening. The nuclear in stellar cores is the same process that powers hydrogen bombs, but stars manage to control and sustain these reactions for eons. Deep in the sun's core, 4 hydrogen nuclei combine to create one helium nucleus, releasing tremendous amounts of energy in the process. This energy slowly works its way from the core to the surface, taking hundreds of thousands of years to complete the journey. The light leaving the sun today actually began its journey in the solar core during the last ice age on Earth. Some stars live solitary lives like our sun, but many exist in binary or multiple star systems where 2 or more stars orbit around each other. These stellar partnerships can create spectacular cosmic dances, with stars exchanging material or even merging together in catastrophic events. In some binary systems, one star may steal gas from its companion, gradually growing more massive over time. When enough material accumulates, it can trigger explosive events called novae, where the surface of the star erupts in a brilliant flash visible from thousands of light years away. The night sky appears static to our eyes, but stars are actually moving through space at tremendous speeds. Our sun, along with the entire solar system, is racing through the galaxy at about 200 kilometers per second. Other stars have their own motions, creating a slow cosmic shuffle that gradually changes the patterns of constellations over thousands of years. The Big Dipper that we see today looked quite different to early humans, and it will continue evolving as the stars within it follow their individual paths through space. Stars also rotate as they travel through the galaxy, some spinning much faster than others. The sun completes one rotation about every 25 days, but some neutron stars spin hundreds of times per second, faster than a kitchen blender. Young, massive stars often rotate so rapidly that they become flattened into oblate spheres, wider at their equators than at their poles. This rapid rotation can affect how they age and eventually die, influencing the types of elements they create and scatter back into space. Variable stars change their brightness over time, pulsating like cosmic lighthouses as they expand and contract. Cepheid variables brighten and dim with clockwork regularity, their periods of variation directly related to their intrinsic brightness. This relationship makes them incredibly useful as cosmic distance markers, allowing astronomers to measure how far away distant galaxies are located. By observing how bright a Cepheid appears compared to how bright it should be, scientists can calculate its distance with remarkable precision. Some stars experience sudden, dramatic changes in brightness called stellar flares. These explosive events can temporarily increase a star's luminosity by factors of thousands or even millions. Red dwarf stars are particularly prone to powerful flares that can strip away the atmospheres of any nearby planets. If such a flare occurred on a red dwarf with potentially habitable worlds, it could sterilize those planets in minutes, making red dwarfs somewhat problematic hosts for life, despite their incredibly long lifespans. The magnetic fields surrounding stars create beautiful and complex phenomena. Solar prominences arch hundreds of thousands of kilometers above the sun's surface, following invisible magnetic field lines like cosmic aurora. These magnetic structures can become twisted and tangled, eventually snapping and releasing enormous amounts of energy in solar flares. When these eruptions are directed toward Earth, they can disrupt satellite communications and create spectacular displays of northern and southern lights in our atmosphere. Stars influence their cosmic neighborhoods in profound ways, sculpting the space around them with their radiation and stellar winds. Young, hot stars emit intense ultraviolet light that ionizes nearby gas clouds, causing them to glow like cosmic neon signs. These emission nebulae can shine for millions of years, their colors determined by the specific elements being excited by the stellar radiation. The Orion Nebula, visible to the naked eye as a fuzzy star in the constellation Orion, is one of the most famous examples of a star-forming region illuminated by its own newborn stars. The elements that make up our bodies and our world were created inside the cores of ancient stars through nuclear fusion. Stars begin by fusing hydrogen into helium, but as they age and their cores become hotter and denser, they can create progressively heavier elements. Carbon, nitrogen, oxygen, and all the elements up to iron on the periodic table are forged in the nuclear furnaces of stellar cores. We are literally made of stardust, our atoms carrying the history of cosmic evolution within them. When a star reaches the end of its hydrogen fuel supply, it begins one of the most dramatic transformations in the universe. The delicate balance that sustained it for billions of years starts to shift, and gravity begins to win the ancient battle. As the core contracts and heats up, the star enters its final act, a period that can be both spectacular and surprisingly gentle, depending on the star's original mass. Medium-sized stars like our Sun will eventually expand into red giants, swelling to enormous proportions as their outer layers cool and extend far beyond their original boundaries. During this phase, the Sun will grow so large that it will likely engulf Mercury and Venus, while Earth bakes under the intense heat of our dying star. Yet this expansion happens gradually over millions of years, a slow cosmic farewell rather than a sudden catastrophe. The red giant phase allows the star to fuse helium into heavier elements, creating carbon and oxygen in its core while shedding its outer layers into space in beautiful, ghostly shells called planetary nebulae. The most massive stars face a far more violent end. When they exhaust their nuclear fuel, they cannot gently shed their outer layers like smaller stars. Instead, their cores collapse catastrophically in less than a second, creating temperatures and pressures so extreme that they trigger a supernova explosion. These stellar detonations can outshine entire galaxies for weeks or months, releasing more energy in a few seconds than our sun will produce in its entire 10 billion year lifetime. The shock waves from supernovae race outward at thousands of kilometers per second, heating and compressing nearby gas clouds and often triggering the formation of new stars. Supernovae are responsible for creating and dispersing the heaviest elements in the universe. The incredible energies involved in these explosions forge elements heavier than iron, including the gold in jewelry, the silver in coins, and the uranium used in nuclear power. These precious metals literally cannot be created anywhere else in the universe except in the final moments of a massive star's life. Every atom of gold on Earth was forged in the heart of an exploding star billions of years ago, making these metals not just rare and valuable, but truly cosmic treasures. The remnants left behind after stellar death are among the most extreme objects in the universe. When a medium-sized star exhausts its fuel and sheds its outer layers, it leaves behind a white dwarf, a stellar corpse about the size of Earth but containing the mass of the Sun. These incredibly dense objects are so compact that a teaspoon of white dwarf material would weigh as much as a car. White dwarfs shine not from nuclear fusion, but from leftover heat from their formation, slowly cooling over billions of years like cosmic embers in the darkness. More massive stars leave behind even stranger remnants. When a star more than 20 times the mass of the Sun explodes as a supernova, its core may collapse into a neutron star, an object so dense that atomic nuclei are crushed together, like dishes in a cosmic sarcan. A neutron star packs more mass than the Sun into a sphere only about 20 kilometers across. The surface gravity is so intense that a person standing on a neutron star would weigh as much as a mountain, and the magnetic fields are trillions of times stronger than Earth's. Some neutron stars emit regular pulses of radiation as they spin, sweeping beams of energy across space like cosmic lighthouses. These pulsars were first discovered in the 1960s, and their incredibly regular pulses initially led some scientists to wonder if they might be signals from extraterrestrial civilizations. The pulses are so precise that they rival atomic clocks in their accuracy, allowing astronomers to use pulsars as natural laboratories for studying extreme physics and even detecting gravitational waves. The most massive stars of all may collapse into black holes, regions of space-time where gravity becomes so strong that nothing, not even light, can escape. These cosmic monsters warp the fabric of space and time around them, creating effects that seem to defy common sense. Time itself slows down near a black hole, and objects falling toward the event horizon appear to freeze from the perspective of distant observers. Yet black holes are not cosmic vacuum cleaners despite their fearsome reputation. They only affect objects that venture very close to them, and from a safe distance they exert no more gravitational pull than the original star that collapsed to create them. Stellar death is not truly an ending, but rather a transformation that enriches the universe and enables new generations of stars and planets to form. The heavy elements created in stellar cores and scattered by supernovae become the raw materials for rocky planets like Earth. The shock waves from exploding stars compress nearby gas clouds, triggering the birth of new stars. In this way, stellar death and birth are intimately connected, part of an endless cosmic cycle that had continued for over 13 billion years. Binary star systems can create even more exotic scenarios when one of the partners dies. If a white dwarf has a companion star close enough to steal material from, the stolen gas can accumulate on the white dwarf's surface until it reaches critical density and temperature. When this happens, the entire surface of the white dwarf explodes in a thermonuclear blast called a nova. Unlike supernova, which destroy the star entirely, novae allow the white dwarf to survive and potentially repeat the process millions of years later. Some binary systems contain two white dwarfs that slowly spiral toward each other, losing energy by emitting gravitational waves. When they finally merge, the combined mass may exceed the limit that white dwarf can support, triggering a type Ia supernova. These explosions are remarkably consistent in their brightness, making them valuable tools for measuring cosmic distances and studying the expansion of the universe. The discovery that the universe's expansion is accelerating, leading to the Nobel Prize-winning conclusion that dark energy exists, relied heavily on observations of these stellar explosions. Even in death, stars continue to influence their cosmic neighborhoods for millions of years. Supernova remnants expand outward as glowing shells of hot gas, sweeping up material and creating cavities in the interstellar medium. These blast waves can remain visible for thousands of years, creating some of the most beautiful and complex structures in the galaxy. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in the year 1054, still glows brightly today and contains a pulsar spinning 30 times per second at its center. The study of stellar evolution helps us understand not only how stars live and die, but also how the universe itself has evolved over cosmic time. The first stars that formed after the Big Bang were made almost entirely of hydrogen and helium, the only elements that existed in the early universe. These population 3 stars, as astronomers call them, were probably much more massive than typical stars today, living fast and dying young in spectacular supernovae that scattered the first heavy elements into space. Each subsequent generation of stars has been enriched with more heavy elements, allowing for the formation of rocky planets and, eventually, life as we know it. Our Sun is considered a population 1 star, enriched with elements from many previous generations of stellar death and rebirth. The calcium in our bones, the iron in our blood, and the oxygen we breathe were all created in the nuclear furnaces of ancient stars and scattered into space by their dying breaths. Star formation continues today in giant molecular clouds throughout our galaxy, but the process has slowed considerably compared to the universe's youth. The Milky Way now creates only a few new stars each year, down from possibly hundreds per year in its early history. As the universe ages and expands, star formation will continue to decline, and eventually, in the distant future, no new stars will be born at all. The life cycle of stars operates on timescales almost impossible for humans to comprehend. The smallest red dwarf stars may continue burning hydrogen for trillions of years, far longer than the universe has currently existed. When the last red dwarf finally exhausts its fuel and fades away, it will mark the end of the stellar age, leaving behind a cold, dark universe populated only by stellar remnants and the slowly evaporating black holes. Yet for now, on this small planet orbiting an ordinary yellow star, we can look up at the night sky and see the cosmic story written in starlight. Every point of light represents a nuclear furnace burning in the darkness, creating the elements of life and scattering them into space. We are not separate from this cosmic drama, but intimately connected to it. Temporary arrangements of stardust that have somehow learned to contemplate the stars from which we came. The distances between stars stretch beyond human imagination, measured in units that dwarf our earthly experience. Light itself, racing at 300,000 kilometers per second, takes years to travel from the nearest stars to our eyes. Proxima Centauri, our closest stellar neighbor, lies over 4 light-years away. If you could drive a car at highway speeds toward this distant sun, the journey would take more than 40 million years. Even at the speed of our fastest spacecraft, reaching Proxima Centauri would require tens of thousands of years of continuous travel through the cosmic void. This vast emptiness between stars means that stellar collisions are incredibly rare events, despite the billions of stars crowded into our galaxy. When galaxies themselves collide, as the Milky Way and Andromeda will in about 4 billion years, the individual stars pass by each other like ships in the night. The spaces between them are so enormous that direct stellar impacts occur perhaps once in a trillion years. It is a reminder that space truly lives up to its name, consisting mostly of empty vacuum punctuated by tiny islands of matter and energy. The light reaching our eyes tonight began its journey years, decades, or even centuries ago. When you look at Polaris, the North Star, you see it as it appeared over 400 years ago, around the time of Shakespeare. The stars of the Big Dipper show us light that left their surfaces between 80 and 120 years ago. In this way, stargazing becomes a form of time travel, allowing us to peer into the cosmic past with nothing more than our naked eyes. The night sky is not a snapshot of the present, but a museum of stellar history spread across the dome of darkness above us. Some stars vary their brightness in patterns so regular that ancient civilizations used them as celestial clocks. Algol, known to medieval astronomers as the demon star, dims noticeably every 2 days and 20 hours as a fainter companion star passes in front of it. This eclipsing binary system was one of the first variable stars recognized by human observers, its mysterious winking earning it an ominous reputation among early stargazers. Today we understand that Algol's dimming is simply a cosmic shadow, but its reliable rhythm continues to mark time as it has for thousands of years. Other variable stars pulsate intrinsically, swelling and contracting like cosmic hearts beating in slow motion. Delta Cephei, the prototype of the Cepheid variables, brightens and dims over a period of 5 days and 9 hours with clockwork precision. These stellar timepieces helped astronomers unlock one of the universe's greatest mysteries, revealing that the spiral nebulae visible in telescopes were actually distant galaxies, far beyond the boundaries of our own Milky Way. The discovery expanded our conception of the cosmos almost overnight, transforming the universe from a single galaxy to an ocean containing billions of island universes. Binary and multiple star systems create some of nature's most spectacular displays when viewed through telescopes. Alboreo, the head star of the constellation Cygnus the Swan, reveals itself as a beautiful double star when magnified, showing a golden primary star paired with a blue companion. The color contrast creates a stunning celestial jewel box effect that has delighted amateur astronomers for generations. These stellar partnerships remind us that our solitary sun is somewhat unusual, as most stars in the galaxy exist in gravitationally bound relationships with one or more companions. Some binary systems are so close that their outer atmospheres actually touch, creating common envelope binaries where material flows freely between the two stars. Others are contact binaries, figure 8-shaped objects where two stars have merged their outer layers while maintaining separate cores. These exotic configurations can lead to spectacular outbursts when material transfers between the components, or when tidal forces trigger enhanced stellar activity. The resulting light curves and spectral variations provide astronomers with natural laboratories for studying stellar physics under extreme conditions. The magnetic fields of stars create invisible architectures that shape their behavior in profound ways. Solar flares and coronal mass ejections from our own sun demonstrate the power of stellar magnetism on a scale we can observe and measure. More exotic magnetic stars, called magnetars, possess fields trillions of times stronger than Earth's, capable of warping the very atoms in their vicinity. If a magnetar existed where our moon orbits, its magnetic field would be strong enough to erase every credit card on Earth's surface. These magnetic monsters occasionally release energy bursts so intense they can be detected by satellites throughout the solar system. Some stars display magnetic activity cycles similar to our sun's 11-year sunspot cycle, but on vastly different timescales. Young stars may experience magnetic storms thousands of times more powerful than anything our sun produces, while older stars often settle into long periods of magnetic quiet. The interaction between stellar rotation, convection, and magnetic fields creates a complex dynamo effect that varies from star to star. Understanding these magnetic cycles helps astronomers predict which stars might be hospitable to planetary systems and potential life. The rotation rates of stars reveal fascinating stories about their formation and evolution. Newly formed stars often spin rapidly, rotating in hours rather than weeks like our mature sun. As stars age, they gradually slow down through magnetic braking, where stellar winds carry away angular momentum over millions of years. Some ancient stars rotate so slowly that their rotation periods exceed our sun's by factors of 10 or more. The measurement of stellar rotation provides astronomers with another tool for determining stellar ages and understanding how planetary systems evolve over time. Stellar winds, streams of charged particles flowing outward from stellar surfaces, carve cavities in the surrounding interstellar medium and influence the formation of new stars. Massive stars produce particularly powerful winds that can clear out regions dozens of light years across, creating stellar wind bubbles visible in infrared and radio wavelengths. These winds carry away significant amounts of stellar mass over millions of years, influencing how stars evolve and ultimately determining their final fate. Wolf-Rayet stars, among the most massive and luminous stars known, lose material so rapidly through stellar winds that they may shed several Earth masses worth year. The of material, every spectra of starlight contain detailed fingerprints that reveal stellar composition, temperature, pressure, and motion. Each chemical element absorbs or emits light at specific wavelengths, creating dark absorption lines or bright emission lines that astronomers can identify and measure. These stellar fingerprints allow us to determine that stars throughout the galaxy are made of the same elements found on Earth, providing evidence for the fundamental unity of cosmic chemistry. The strength and width of spectral lines reveal stellar temperatures and densities, while tiny shifts in wavelength indicate whether stars are moving toward or away from us through space. Some stars exhibit unusual spectral characteristics that hint at exotic compositions or extreme physical conditions. Carbon stars show enhanced carbon absorption features in their spectra, indicating atmospheres enriched with carbon produced by nuclear burning in their cores. Barium stars display unexpected concentrations of heavy elements that suggest they have received material from evolved companion stars. These chemical peculiarities provide clues about stellar evolution processes that cannot be directly observed, allowing astronomers to piece together the hidden histories of stellar systems. Brown dwarfs occupy the fuzzy boundary between stars and planets, massive enough to fuse some nuclear fuel but too small to sustain hydrogen burning like true stars. These failed stars glow primarily from the heat of their gravitational contraction, slowly cooling and dimming over billions of years. Some brown dwarfs are warm enough to have weather patterns in their atmospheres, with clouds of iron and silicate minerals creating variable brightness as they rotate. The discovery of brown dwarfs filled a long predicted gap in the cosmic inventory, confirming theoretical models of star formation while raising new questions about the minimum mass required for stellar ignition. The coolest brown dwarfs have surface temperatures similar to a hot oven, making them among the coldest objects capable of nuclear fusion. Some may even have water clouds in their upper atmospheres, creating environments more similar to gas giant planets than to traditional stars. These objects challenge our definitions of stars and planets, existing in a transitional realm where the boundaries between different classes of cosmic objects become beautifully blurred. Future space telescopes may discover brown dwarfs cool enough to support complex atmospheric chemistry, possibly even organic molecules in their outer layers. Stellar formation continues in our galaxy today, though at a much reduced rate compared to the universe's youth. Giant molecular clouds, some containing enough material to create millions of stars, drift through the galactic disk like cosmic seedbeds waiting for the right trigger to begin the star formation process. Spiral density waves, supernova shock fronts, or gravitational interactions with other clouds can compress these regions enough to initiate gravitational collapse. Once started, star formation often proceeds in waves, with the first massive stars to form triggering additional collapse through their intense radiation and eventual supernova explosions. The efficiency of star formation varies dramatically from one molecular cloud to another, with some regions converting only a small percentage of their gas into stars, while others undergo rapid, intensive bursts of stellar birth. Understanding these variations helps astronomers predict how galaxies will evolve over cosmic time and whether the universe will eventually run out of raw materials for making new stars. Current observations suggest that star formation peaked in the universe roughly 10 billion years ago and has been declining ever since, though at a rate slow enough that new stars will continue forming for many billions of years to come. Young star clusters provide natural laboratories for studying stellar evolution because all their member stars formed at approximately the same time from the same initial cloud of gas and dust. The Pleiades cluster, visible to the naked eye as a fuzzy patch in the constellation Taurus, contains hundreds of hot blue stars that are only about 100 million years old, practically newborns on cosmic timescales. Observations of such clusters allow astronomers to test theories of stellar evolution by comparing stars of different masses at the same evolutionary stage. Globular clusters represent the opposite extreme, containing some of the oldest stars in our galaxy. These spherical collections of hundreds of thousands of ancient red and yellow stars formed when the Milky Way was young, before the galactic disk had taken its current shape. The stars in globular clusters are metal poor, meaning they contain very few elements heavier than hydrogen and helium, reflecting the chemical composition of the early universe before generations of stellar nucleosynthesis had enriched the interstellar medium with heavy elements. Open clusters like the Hyades and the Beehive cluster are looser associations of stars that formed more recently in the galactic disk. These clusters gradually disperse over hundreds of millions of years as gravitational interactions and tidal forces from the galaxy slowly pull their member stars apart. Our own sun may have formed in such a cluster billions of years ago, though its siblings have long since scattered throughout the galaxy. Searching for the sun's lost family members remains an ongoing challenge in stellar archaeology. The study of stellar populations helps astronomers understand how galaxies form and evolve over cosmic time. Population 1 stars like our Sun are relatively young and metal-rich, formed from gas that had been enriched by previous generations of stellar nucleosynthesis. Population 2 stars are older and metal-poor, representing an earlier epoch when the galaxy contained fewer heavy elements. The hypothetical population 3 stars, which have never been directly observed, would represent the very first generation of stars formed from primordial hydrogen and helium in the early universe. These primordial stars were probably much more massive than typical stars today, perhaps reaching several hundred solar masses. Their immense size meant they burned through their nuclear fuel extremely rapidly, living only a few million years before exploding as pair instability supernovae that completely destroyed the star and scattered the first heavy elements into the cosmos. Finding evidence of these first stars remains one of the holy grails of modern astronomy, as they hold the key to understanding how the universe transitioned from its simple initial state to the chemically complex cosmos we observe today. The search for these ancient stellar giants continues to drive some of astronomy's most ambitious projects. Next-generation telescopes are designed to peer deeper into space and further back in time, hoping to catch glimpses of the universe when it was only a few 100 million years old. At such distances, we would see these primordial stars not as they are now, but as they were in their brief, brilliant youth, before they enriched the cosmos with the elements that would eventually make rocky planets and life possible. The light from stars carries more than just illumination across the vast distances of space. It carries information, stories written in wavelengths of electromagnetic radiation that tell us about stellar temperatures, compositions, velocities, and magnetic fields. Each photon that reaches our instruments has traveled for years, decades, or millennia through the cosmic void, maintaining its message intact across unimaginable distances. In a very real sense, astronomers are cosmic archaeologists, decoding these ancient light messages to reconstruct the history of stars and galaxies. Stellar spectroscopy reveals that stars are not uniform balls of gas, but complex, layered objects with distinct regions where different physical processes dominate. The photosphere, the visible surface of a star, is where most of the light we see originates. Above it lies the chromosphere, a thin layer where temperatures actually increase with altitude, defying our everyday experience that things get cooler as we move away from a heat source. Beyond that stretches the corona, a tenuous atmosphere heated to millions of degrees by processes we still don't fully understand. The sun's corona becomes visible during total solar eclipses when the moon blocks the brilliant photosphere and reveals the gossamer streamers of hot gas extending millions of kilometers into space. These coronal structures follow the invisible architecture of magnetic field lines, creating shapes that change over the solar cycle as magnetic activity waxes and wanes. Other stars presumably have similar corona, though they remain largely invisible to our current instruments due to the overwhelming brightness of stellar photospheres. Stellar oscillations provide another window into stellar interiors, allowing astronomers to probe the hidden layers beneath a star's surface. Just as seismologists use earthquake waves to map Earth's internal structure, stellar seismologists study the subtle pulsations that ripple through stellar atmospheres. These oscillations are caused by sound waves bouncing around inside the star, creating interference patterns that modulate the star's brightness with periods ranging from minutes to hours. The sun exhibits thousands of different oscillation modes, each providing information about conditions at different depths within the solar interior. The field of astroseismology has revealed that stellar interiors are far more dynamic than previously imagined. Convection currents, rotation, and magnetic fields create complex three-dimensional structures that influence how stars age and evolve. Some stars show evidence of rapid rotation in their cores, while their surfaces rotate much more slowly, suggesting that magnetic fields may decouple different layers within the stellar interior. Others display mixing processes that transport elements from deep within the star to the surface, changing their observable properties over time. Red giant stars undergo particularly dramatic internal changes as they age. When hydrogen burning in the core ceases, the core contracts and heats up while the outer layers expand and cool. This creates a shell of hydrogen burning around an inert helium core, fundamentally altering the star's structure. The convective zone that carries energy outward from the core expands dramatically, sometimes reaching all the way to the surface, and dredging up material that was processed by nuclear reactions deep in the stellar interior. During this red giant phase, stars can become thousands of times more luminous than they were on the main sequence, even though their surface temperatures decrease. This paradox occurs because the stellar radius increases so dramatically that the total surface area more than compensates for the lower temperature. A red giant star might swell to a size larger than Earth's orbit around the Sun, yet have a surface temperature cooler than a candle flame. The transition from main sequence star to red giant happens relatively quickly on cosmic timescales, sometimes taking only a few million years. This rapid evolution means that red giants are relatively rare compared to main sequence stars, even though every star more massive than about half the Sun's mass will eventually go through this phase. The rarity of red giants in the night sky reflects their brief evolutionary stage rather than any fundamental scarcity in star formation. Some red giants experience thermal pulses, episodes of unstable helium burning that can dramatically change their luminosity and surface composition over thousands of years. During these events, the star may eject material in powerful stellar winds, creating expanding shells of gas that eventually become planetary nebulae. These ghostly rings and bubbles of glowing gas represent the final exhalations of dying stars, returning processed material to the interstellar medium where it can eventually be incorporated into new generations of stars and planets. The most spectacular planetary nebulae display intricate structures that rival the most beautiful works of art, The Ring Nebula, the Cat's Eye Nebula, and the Helix Nebula show complex patterns of knots, jets, and spiral features that reveal the chaotic final stages of stellar evolution. These structures are sculpted by stellar winds, magnetic fields, and possibly the gravitational influence of unseen companion stars or planets. Each planetary nebula is unique, reflecting the individual history and star. The circumstances of its central stars of planetary nebulae are among the hottest objects in the universe, with surface temperatures that can exceed 100,000 degrees. These white dwarf stars are so hot that they emit most of their energy as ultraviolet radiation, which ionizes the surrounding nebular gas and causes it to glow in the visible light we observe. As these stellar remnants slowly cool over billions of years, they will eventually become too faint to illuminate their surrounding nebulae, leaving behind invisible white dwarf stars orbiting through space like cosmic ghosts. White dwarf stars represent the final fate of roughly 90% of all stars, including our own sun. These stellar corpses pack about 60% of the sun's mass into a sphere roughly the size of Earth, creating matter so dense that a sugar cube-sized sample would weigh as much as an automobile. The electrons in white dwarf material are forced into a quantum mechanical state called degeneracy, where they resist further compression through a pressure that has no analog in everyday experience. The maximum mass that a white dwarf can support, known as the Chandrasekhar limit, is about 1.4 times the mass of the Sun. This fundamental limit, discovered by the young astrophysicist Subrahmanyan Chandrasekhar in the 1930s, determines the boundary between white dwarf formation and more exotic stellar endpoints. Stars that would leave behind white dwarfs more massive than this limit must find another way to shed mass during their evolution, or they will collapse into neutron stars or black holes instead. The surfaces of white dwarf stars are among the most chemically pure environments known to exist. The intense gravitational field causes heavy elements to sink toward the center, while lighter elements float to the surface, creating atmospheres composed almost entirely of hydrogen or helium. Some white dwarfs show evidence of having accreted heavier elements from their surroundings, possibly from the destruction of asteroids or comets that wandered too close to the stellar remnant. Crystallization occurs in the cores of white dwarf stars as they cool, creating cosmic diamonds larger than Earth. The carbon and oxygen nuclei in the stellar interior arrange themselves into crystalline lattices when the temperature drops below about 10 million degrees, a process that releases latent heat and slows the cooling rate. This crystallization phase can last for billions of years, during which the white dwarf maintains a nearly constant luminosity before resuming its gradual fade into darkness. The coolest white dwarf stars provide natural laboratories for studying matter under extreme conditions that cannot be reproduced on Earth. Their magnetic fields can be millions of times stronger than our planet's, while their gravitational redshift measurably affects the wavelengths of light escaping from their surfaces. Some white dwarfs pulsate as they cool, creating variable stars that help astronomers probe the interior structure of these dense stellar remnants through astroseismological techniques. Binary white dwarf systems may eventually merge through the emission of gravitational waves, creating some of the most energetic explosions in the universe. When two white dwarfs spiral together, their combined mass may exceed the Chandrasekhar limit, triggering a thermonuclear explosion that completely destroys both stars. These type Ia supernovae are so bright they can be seen across billions of light years, and their remarkably consistent peak luminosity makes them valuable tools for measuring cosmic distances and studying the expansion of the universe. The discovery that the universe's impulse expansion is accelerating, the existence of dark energy, relied heavily on observations of distant type Ia supernovae. These stellar explosions serve as standard candles, objects whose intrinsic brightness is known, allowing astronomers to determine their distances by comparing their apparent brightness to their absolute luminosity. The finding that distant supernovae appear fainter than expected in a decelerating universe led to one of the most surprising discoveries in modern cosmology. Some white dwarf stars exist in close binary systems where they can accrete material from a companion star, gradually gaining mass over millions of years. This accretion process can lead to nova explosions when enough hydrogen accumulates on the white dwarf's surface to trigger runaway nuclear fusion. Unlike supernovae, which destroy the star entirely, novae leave the white dwarf intact and capable of repeating the process, creating recurrent novae that flare up every few decades or centuries. The most extreme accretion scenarios can create some of the most luminous objects in the local universe. When a white dwarf accretes material at just the right rate, it can sustain steady nuclear burning on its surface, creating a super soft X-ray source that outshines normal stars by factors of thousands. These systems represent a delicate balance between accretion rate and nuclear burning, and small changes in the mass transfer rate can cause dramatic variations in their X-ray output. Neutron stars represent an even more extreme form of stellar death, created when stars more than 8 to 10 times the mass of the Sun exhaust their nuclear fuel and undergo core collapse. The collapse is so rapid and violent that the core rebounds, sending a shock wave outward that tears the star apart in a supernova explosion visible from billions of light years away. What remains is a stellar remnant so dense that atomic nuclei are crushed together like sardines in a cosmic can, creating matter unlike anything found elsewhere in the universe. A neutron star packs more mass than the Sun into a sphere only about 20 kilometers across, creating gravitational fields so intense that the escape velocity from the surface approaches half the speed of light. The surface gravity is about 100 billion times stronger than Earth's, meaning that a marshmallow dropped onto a neutron star would impact with the energy of an atomic bomb. Time dilation effects are so strong that clocks on the neutron star surface would run noticeably slower than those in orbit around it. The magnetic fields of neutron stars can be trillions of times stronger than Earth's magnetic field, intense enough to distort the shapes of atoms themselves. These magnetic fields channel radiation into narrow beams that sweep across space as the neutron star rotates, creating the lighthouse effect we observe as pulsars. The most rapidly spinning pulsars rotate hundreds of times per second, with timing precision that rivals atomic clocks, making them valuable tools for testing theories of gravity and detecting gravitational waves. Some neutron stars, called magnetars, possess magnetic fields so strong that they can trigger starquakes that release more energy in 1/10 of a second than the Sun produces in a year. These magnetic field reconfigurations can crack the neutron star's crust and accelerate particles to near light speed, creating gamma ray bursts that can be detected throughout the galaxy. A magnetar flare occurring within 10 light years of Earth could potentially damage our ozone layer and trigger a mass extinction event. The interior structure of neutron stars remains largely theoretical, as the matter densities involved exceed those found in atomic nuclei. The outer crust likely consists of atomic nuclei immersed in a sea of degenerate electrons, while deeper layers may contain exotic forms of matter including hyperons, kaons, and possibly even quark matter. The core might exist in a superfluid state where neutrons flow without friction, creating internal dynamics that could explain pulsar glitches and timing irregularities. Neutron star mergers, detected through gravitational waves and electromagnetic observations, have revolutionized our understanding of how heavy elements are created and distributed throughout the universe. When two neutron stars spiral together and collide, they create conditions even more extreme than supernova explosions, forging elements like gold, platinum, and uranium through rapid neutron capture processes. These be responsible, nova events may for producing most of the gold and other precious metals found on Earth and throughout the cosmos. The gravitational waves emitted by merging neutron stars provide a completely new way of studying these exotic objects, complementing traditional electromagnetic observations with information about their masses, spins, and internal structure. The detection of gravitational waves from neutron star mergers has confirmed predictions of Einstein's general relativity, while opening new windows into fundamental physics under conditions that cannot be replicated in any Earth-based laboratory. Black holes represent the ultimate endpoint of stellar evolution for the most massive stars, objects so dense that they create tears in the fabric of space-time itself. When a star more than 20 to 30 times the mass of the Sun reaches the end of its nuclear burning lifetime, no known force can prevent its complete gravitational collapse. The stellar core shrinks beyond the neutron degeneracy pressure that supports neutron stars, continuing to contract until it forms a singularity where the laws of physics as we know them break down. The event horizon surrounding a black hole marks the boundary beyond which nothing, not even light, traveling at 300,000 kilometers per hour second, can escape the gravitational pull. This invisible surface defines the black hole's size, which depends only on its mass through a surprisingly simple relationship. A black hole with the mass of our Sun would have an event horizon only about 6 kilometers in diameter, while a black hole containing 1 million solar masses would span roughly 3 million kilometers, still smaller than our Sun's visible surface. Contrary to popular misconceptions, black holes do not act like cosmic vacuum cleaners, sucking in everything around them. From a safe distance, a black hole exerts no more gravitational attraction than the original star that collapsed to form it. If our Sun were somehow replaced by a black hole of equal mass, Earth would continue orbiting normally, though the planet would quickly freeze without solar energy. Black holes enlionate their DOM environment within a few times their event horizon radius, beyond which their gravity behaves like that of any other massive object. The space around a black hole becomes increasingly distorted as matter approaches the event horizon, creating effects that seem to violate common sense. Time dilation becomes so extreme near the event horizon that an outside observer would see infalling matter appear to slow down and freeze at the boundary, its light redshifted to longer and longer wavelengths until it fades from view. From the perspective of someone falling into the black hole, however, the journey across the event horizon happens in a finite time, though tidal forces would likely tear apart any real object long before it reached the singularity. Rotating black holes, which probably represent the majority of stellar mass black holes in the universe, create even more exotic space-time geometries through a phenomenon called frame dragging. The spinning mass literally drags the surrounding space-time along with it, creating a region called the ergosphere where nothing can remain at rest relative to distant observers. This rotation stores enormous amounts of energy that could theoretically be extracted through various mechanisms, making rotating black holes potential power sources for advanced civilizations. The study of stellar evolution continues to reveal new surprises and complexities as observational techniques improve and theoretical models become more sophisticated. Each new generation of telescopes and detectors opens fresh windows into stellar physics, from the discovery of exoplanets orbiting other stars to the detection of gravitational waves from colliding stellar remnants. The story of stars is far from complete, with many chapters yet to be written as we probe deeper into the cosmos and further back in cosmic time. Understanding stars is ultimately about understanding ourselves and our place in the universe. The elements in our bodies, the energy that powers our civilization, and the very existence of planets capable of supporting life all depend on the nuclear furnaces burning in stellar cores throughout the galaxy. We are quite literally children of the stars, temporary arrangements of stellar ash that have somehow learned to contemplate the cosmos from which we emerged. As you drift towards sleep tonight, carried by the gentle rhythm of stellar stories, remember that the atoms flowing through your bloodstream were forged in the hearts of ancient suns. The calcium in your bones was created in a supernova explosion billions of years ago. The iron carrying oxygen through your circulatory system was synthesized in the core of a dying massive star. You are not separate from the cosmic drama unfolding in the night sky above, but an integral part of it, a brief flowering of stellar material that has achieved consciousness and wonder. The stars continue their ancient dance overhead, burning hydrogen into helium, creating the elements of life, and slowly evolving through their destined life cycles. Some will shine steadily for billions of years, while others will explode spectacularly, seeding space with heavy elements for future generations of stars and planets. In this endless cycle of stellar birth, evolution, and death, new worlds are constantly being born while others fade into cosmic history. Let these stellar stories carry you gently into dreams where time moves differently and distances collapse into manageable journeys. In sleep, you might find yourself drifting among the stellar nurseries where new suns are born, or floating peacefully around red giant stars as they shed their outer layers into space. The universe of stars awaits your dreaming mind, ready to reveal its secrets in the quiet language of rest and wonder. The night sky holds secrets that stretch far beyond what our eyes can see. Hidden among the familiar constellations are stellar phenomena so strange and beautiful that they challenge our understanding of what stars can become. Some stars pulse with mathematical precision, their brightness rising and falling like cosmic heartbeats. Others undergo sudden transformations that can be seen from billions of miles away, flaring to life in spectacular displays that outshine entire galaxies for brief moments. Cataclysmic variable stars represent some of the most dramatic stellar partnerships in the universe. These systems consist of a white dwarf stealing material from a nearby companion star, gradually accumulating hydrogen on its surface until the conditions become ripe for explosion. When the stolen gas reaches critical temperature and density, the entire surface of the white dwarf ignites in a thermonuclear flash that can increase the system's brightness by factors of thousands or even millions. These nova explosions are visible to the naked eye when they occur in nearby stars, appearing as new stars that suddenly blaze forth in previously empty patches of sky. The word nova itself means new star, reflecting the ancient belief that these events represented the birth of celestial objects. We now understand that novae are actually stellar resurrections, white dwarf stars that repeatedly undergo surface explosions while remaining fundamentally unchanged. Some novae are recurrent, flaring up every few decades as they accumulate fresh material from their companions. Others may remain dormant for thousands of years between outbursts, making their prediction nearly impossible, despite our growing understanding of the underlying physics. Classical novae can eject material at speeds of thousands of kilometers per second, creating expanding shells of hot gas that remain visible for years after the initial explosion. These nova remnants provide natural laboratories for studying high-energy astrophysics, showing how matter behaves under extreme conditions of temperature, density, and magnetic field strength. The expanding shock waves can trigger chemical reactions that create complex molecules in space, contributing to the cosmic inventory of organic compounds that may eventually find their way into planetary systems. Symbiotic stars represent an even more exotic class of interacting binaries, where a red giant star feeds material to a white dwarf companion over periods of decades or centuries. These systems can undergo both slow nova-like outbursts and more dramatic explosive events, creating some of the most unpredictable variable stars in the galaxy. The interaction between the cool, extended atmosphere of the red giant and the hot, compact white dwarf creates unique spectral signatures that combine absorption lines from both stellar types in a single spectrum. Some symbiotic systems show evidence of jets and outflows that suggest the presence of accretion disks around the white dwarf components. These structures form when material from the donor star doesn't fall directly onto the white dwarf surface, but instead spirals inward while conserving angular momentum. The friction within these accretion disks can heat material to millions of degrees, producing X-ray emission that reveals the hidden dynamics of mass transfer in close binary systems. Wolf-Rayet stars represent a brief but spectacular phase in the evolution of the most massive stars. These objects have lost their outer hydrogen layers through powerful stellar winds, exposing their helium-burning cores to direct observation. Wolf-Rayet stars shine with surface temperatures exceeding 50,000 degrees and emit stellar winds so powerful that they can lose several Earth's masses of material every year. These winds create expanding bubbles of hot gas around the stars, visible as glowing nebulae that reveal the violent environment surrounding these stellar giants. The spectra of Wolf-Rayet stars show broad emission lines from highly ionized elements, indicating that their atmospheres are in constant motion and contain very little hydrogen. This chemical signature reflects the nuclear processing that has occurred in their cores, bringing products of helium burning to the surface where they can be directly observed. Different subtypes of Wolf-Rayet stars show varying amounts of carbon, nitrogen, and oxygen in their spectra, providing clues about the nuclear reactions occurring within their interiors. These massive stars are thought to be the immediate progenitors of some of the most energetic explosions in the universe, and IB and Type 1c supernovae, including Type D, possibly long-duration gamma-ray bursts. When a Wolf-Rayet star finally exhausts its nuclear fuel, the core collapse happens so rapidly that it may form a black hole directly, potentially triggering a hypernova explosion that can outshine billions of normal stars. The connection between Wolf-Rayet stars and gamma-ray bursts remains an active area of research, with implications for understanding the most distant and energetic events observable in the cosmos. Luminous blue variables represent another class of massive, unstable stars that undergo dramatic changes in brightness over human timescales. These stars can vary by several magnitudes over periods of years or decades, sometimes ejecting massive shells of material in violent outbursts. Eta Carinae, perhaps the most famous example, underwent a great eruption in the 1840s that briefly made it one of the brightest stars in Earth's sky, despite being located over 7,000 light-years away. The Great Eruption of Eta Carinae created the distinctive homunculus nebula, a bipolar structure of ejected material that continues expanding at speeds of several hundred kilometers per second. This nebula contains several solar masses of material enriched with heavy elements, representing a significant loss of mass from the original star. The mechanism driving such massive ejections remains poorly understood, but may involve interactions between radiation pressure, stellar rotation, and magnetic fields in the outer layers of extremely luminous stars. Luminous blue variables are thought to be in a transitional phase between main sequence evolution and final core collapse, making them invaluable laboratories for studying the late stages of massive star evolution. Their instability may be caused by the proximity to the Eddington limit, the theoretical maximum luminosity at which radiation pressure exactly balances gravitational attraction. Stars approaching this limit become unstable to small perturbations, potentially explaining the dramatic variability observed in these systems astronomy. Some ears believe that luminous blue variables represent the final phase before Wolf-Rayet evolution, suggesting that the most massive stars may pass through multiple unstable periods before finally exploding as supernova. This evolutionary sequence would help explain the diversity of massive star explosions and the varying amounts of mass loss observed in different stellar populations. The study of these unstable giants provides crucial insights into how the most massive stars live and die, influencing everything from galaxy evolution to the chemical enrichment of the universe. Hypergiant stars push stellar physics to absolute extremes, representing the largest and most luminous stars known to exist. These objects can have radii hundreds of times larger than the Sun and luminosities exceeding 1,000,000 solar luminosities, making them visible from distances of millions of light years. Their immense size means that their surface gravity is actually quite weak, allowing them to lose mass through stellar winds at prodigious rates that would quickly strip away the outer layers of smaller stars. VY Canis Majoris, one of the largest known stars, has a radius so enormous that light takes several hours to travel from one side to the other. If placed at the center of our solar system, this hypergiant would engulf not only all the terrestrial planets, but possibly extend beyond the orbit of Jupiter. Despite its incredible size, VY Canis Majoris has a surface temperature cooler than a candle flame, giving it a deep red color that reflects its status as one of the coolest stars in the galaxy. The asymmetric nebulae surrounding many hypergiant stars suggest that their mass loss is highly structured, possibly influenced by rotation, magnetic fields, or the presence of companion stars. These nebulae show intricate patterns of knots, jets, and spiral features that reveal the complex dynamics occurring in the outer atmospheres of these stellar giants. The study of hypergiant nebulae provides insights into mass loss mechanisms that may be important for understanding how the most massive stars evolve and eventually explode. Red supergiant stars represent a more common but equally impressive class of stellar giants, formed when massive main sequence stars exhaust the hydrogen in their cores and begin burning helium and heavier elements. Betelgeuse, the red supergiant marking Orion's shoulder, is one of the most familiar examples of this evolutionary phase. This star undergoes semi-regular variations in brightness as its outer layers pulsate, sometimes becoming bright enough to rival the brightest stars in Earth's sky. The interior structure of red supergiants is remarkably complex, with multiple shells of nuclear burning creating different elements at various depths within the star. The core may be burning silicon into iron, while surrounding shells burn oxygen, neon, carbon, helium, and hydrogen in concentric layers. This onion-like structure becomes increasingly unstable as the star ages, leading to convective mixing that can transport nuclear processed material to the surface. When red supergiants finally exhaust their nuclear fuel, they undergo some of the most spectacular explosions in the universe. Type 2 supernovae from red supergiant progenitors can briefly outshine entire galaxies, releasing more energy in a few seconds than our sun will produce over its entire lifetime. These explosions are responsible for creating and dispersing many of the heavy elements essential for rocky planet formation and the development of life. The shock waves from supernova explosions race outward at thousands of kilometers per second, heating and compressing the surrounding interstellar medium for thousands of years after the initial explosion. These supernova remnants create some of the most beautiful and complex structures visible in the galaxy, with intricate filaments and shock fronts that reveal the physics of high-energy astrophysics. The Crab Nebula, remnant of a supernova observed by Chinese astronomers in the year 1054, continues to expand and glow nearly 1,000 years after the original explosion. Carbon stars represent a fascinating class of evolved giants whose atmospheres have been enriched with carbon produced by nuclear burning in their cores. These stars appear distinctly red due to the presence of carbon compounds in their outer layers, which absorb blue light more efficiently than red light. Carbon stars are typically found in the later stages of red giant evolution, when convection has dredged up carbon from the stellar interior and transported it to the surface. The atmospheres of carbon stars are chemically reducing environments where carbon monoxide, acetylene, and other carbon-bearing molecules can form and survive. This chemistry is fundamentally different from that found in oxygen-rich stars like our Sun, where oxygen compounds dominate the atmospheric composition. The unusual chemistry of carbon star atmospheres has implications for the types of dust grains they can produce and eject into the interstellar medium. Some carbon stars are surrounded by shells of carbon-rich dust that they have ejected over thousands of years of mass loss. These dust shells can be detected in infrared observations, appearing as extended halos around the central stars. The carbon dust produced by these stars may be an important source of organic compounds in space, potentially contributing to the chemical complexity observed in molecular clouds and planetary systems. S-type stars represent an intermediate class between oxygen-rich and carbon-rich giants, with atmospheric compositions where carbon and oxygen are present in roughly equal abundances. These stars show spectral features of both carbon and oxygen compounds, creating unique that signatures reflect their transitional evolutionary status. S-stars are thought to represent a brief phase in stellar evolution when convective mixing is beginning to transport carbon from the core to the surface, but has not yet made the atmosphere carbon-rich. The study of chemically peculiar stars like carbon stars and S-stars provides insights into the interior processes of evolving giants and the mechanisms that transport nuclear process material from stellar cores to their surfaces. These observations help astronomers test theoretical models of stellar structure and evolution, particularly the complex three-dimensional processes that govern convection and mixing in stellar interiors. Technetium stars represent one of the most direct pieces of evidence for ongoing nuclear reactions in stellar cores. Technetium is a radioactive element with a half-life of only about 200,000 years, meaning that any technetium observed in stellar atmospheres must have been recently produced by nuclear reactions and transported to the surface. The presence of technetium in the spectra of some red giant and carbon stars confirms that these objects are actively burning helium in their cores, and that convective mixing is bringing the products of nuclear burning to their surfaces. The discovery of technetium in stellar atmospheres was a triumph of nuclear astrophysics, providing direct observational evidence for the theoretical prediction that heavy elements are synthesized in stellar cores. This finding helped confirm the role of stars as the cosmic factories responsible for creating most of the elements heavier than hydrogen and helium, supporting the broader theory of stellar nucleosynthesis developed in the mid-20th century. Barium stars represent another class of chemically peculiar objects that show enhanced abundances of elements created by the slow neutron capture process, or S process. These stars are thought to have acquired their unusual through mass composition's transfer from evolved companions that have since become white dwarfs. The barium and other heavy elements observed in these systems were originally synthesized in the asymptotic giant branch phase of the now invisible companion, then transferred to the currently visible star through stellar winds or Roche lobe overflow. The study of barium stars and other chemically peculiar objects provides insights into binary star evolution and the ways that stellar interactions can modify atmospheric compositions. These systems serve as natural laboratories for studying nucleosynthesis processes and the chemical evolution of stellar populations over cosmic time. Flare stars represent a class of magnetically active red dwarf stars that can undergo sudden, dramatic increases in brightness lasting from minutes to hours. These flares are caused by magnetic reconnection events in the stellar corona, similar to solar flares but often much more powerful relative to the star's total luminosity. Some flare stars can increase their brightness by factors of hundreds or thousands during major outbursts, releasing as much energy in a few minutes as the sun produces in several days. The magnetic activity of flare stars is thought to be driven by dynamo processes similar to those operating in the sun, but enhanced by the rapid rotation and deep convection zones characteristic of low-mass stars. Young red dwarfs can rotate much faster than the sun, completing one rotation in hours rather than weeks, which amplifies their magnetic field generation and leads to more frequent and powerful flares. The implications of stellar flares for any planets orbiting these stars are profound. The intense radiation from a major flare could strip away planetary atmospheres or sterilize surface environments, making red dwarf systems potentially hostile to life despite their extremely long main sequence lifetimes. This has important consequences for astrobiology, since red dwarfs are the most common type of star in the galaxy, and many of the potentially habitable exoplanets discovered so far orbit small, active stars. Contact binary stars represent one of the most extreme forms of stellar interaction, where two stars are so close that they actually share a common envelope of material. These systems appear as single, highly distorted stars with figure-8 shapes, where material flows freely between the two stellar cores. Contact binaries are thought to form through the evolution of initially detached binary systems that gradually lose orbital energy and spiral together until their outer atmospheres merge. Ursae Majoris stars are the most common type of contact binary, consisting of two main sequence stars of similar mass that orbit each other with periods of less than 1 day. These systems show continuous variation in brightness as the distorted stellar surfaces rotate in and out of view, creating light curves with distinctive double peaks, corresponding and minimum cross-sectional areas presented to Earth to the maximum. The evolution of contact systems remains an active area of research, with questions about how long such binary configurations can remain stable and what their ultimate fate might be. Some contact binaries may eventually merge to form single, rapidly rotating stars, while others might evolve into more exotic configurations, such as blue straggler stars or helium white dwarfs. Cataclysmic variables encompass a broad class of close binary systems where a white dwarf accretes material from a companion star, leading to periodic outbursts and eruptions. These systems include classical novae, dwarf novae, recurrent novae, and nova-like variables, each representing different aspects of the mass transfer process and accretion physics. The diversity of cataclysmic variable behavior reflects the complex interplay between stellar masses, orbital periods, magnetic fields, and mass transfer rates. Dwarf novae undergo smaller but more frequent outbursts than classical novae, typically increasing in brightness by 2 to 5 magnitudes over periods of days to weeks. These outbursts are thought to be caused by thermal instabilities in the accretion disk around the white dwarf, rather than nuclear explosions on the stellar surface. The cycle of dwarf nova outbursts provides insights into accretion disk physics and the mechanisms that regulate mass transfer in close binary systems. Polars represent a subclass of cataclysmic variables where the white dwarf possesses an extremely strong magnetic field that disrupts the formation of an accretion disk. Instead of spiraling inward through a disk, material from the donor star is channeled directly onto the magnetic poles of the white dwarf, creating hotspots that emit X-rays and cyclotron radiation. The magnetic field strengths in polars can exceed 100 million times Earth's magnetic field, creating some of the most extreme magnetic environments known to exist. Intermediate polars occupy a middle ground between polars and non-magnetic cataclysmic variables, possessing magnetic fields strong enough to disrupt the inner accretion disk, but not powerful enough to prevent disk formation entirely. These systems show complex periodicities reflecting the orbital period, the white dwarf's rotation period, and the beat frequency between the two, creating intricate light curves that reveal the detailed dynamics of magnetically controlled accretion. The study of cataclysmic variables has provided fundamental insights into accretion physics, magnetic field effects, and the evolution of close binary systems. These objects serve as natural laboratories for extreme physics, with conditions of density, temperature, and magnetic field strength that cannot be reproduced in terrestrial experiments. Understanding cataclysmic variables is crucial for interpreting observations of similar accretion processes around neutron stars and black holes. X-ray binaries represent the next step up in accretion-powered systems, where neutron stars or black holes accrete material from companion stars and convert gravitational potential energy into high-energy radiation. These systems can be thousands of times more luminous than cataclysmic variables, with the intense gravitational fields of the compact objects heating infalling material to temperatures of millions of degrees. Low-mass X-ray binaries typically consist of neutron stars or black holes accreting material from main sequence or subgiant companions through Roche lobe overflow. The steady accretion of hydrogen-rich material onto neutron star surfaces can lead to Type 1 X-ray bursts, thermonuclear explosions that briefly outshine the persistent accretion luminosity by factors of hundreds. These bursts provide insights into nuclear physics under extreme conditions and the behavior of matter on neutron star surfaces. High-mass X-ray binaries involve compact objects orbiting massive, luminous companions, such as O or B-type stars. Material is typically accreted from the powerful stellar winds of these hot stars rather than through direct mass transfer, creating different accretion geometries and variability patterns. Some high-mass X-ray binaries are associated with young supernova remnants, suggesting that they formed when one member of a massive binary system exploded as a supernova while the system remained bound. Microquasars represent a special class of X-ray binaries that produce relativistic jets, similar to those observed in active galactic nuclei but on much smaller scales. These jets can extend for light years from the central binary system, carrying FR material at significant actions of the speed of light, and creating radio sources that can be mapped with very high-resolution interferometry. The study of microquasars provides insights into jet formation and collimation mechanisms that may be universal features of accretion onto compact objects. Black hole X-ray binaries offer some of the best opportunities for studying the properties of stellar mass black holes and testing theories of gravity in strong field regimes. These systems can undergo dramatic state changes where the accretion flow transitions between different geometries, producing characteristic changes in X-ray spectra and timing properties. The rapid variability observed in black hole binaries provides information about the space-time geometry near the event horizon and the physics of matter in extreme gravitational fields. Ultraluminous X-ray sources represent a puzzling class of objects that emit more X-ray power than should be possible for stellar mass black holes, accreting at typical rates. These sources, found in nearby galaxies, may represent intermediate mass black holes with masses hundreds to thousands of times that of the Sun. Or they could be stellar mass objects accreting at super Eddington rates through unusual geometries or beaming effects. The diversity of stellar phenomena continues to expand as new observational techniques reveal previously hidden aspects of stellar behavior. Time domain astronomy, the study of how celestial objects change over time, has revolutionized our understanding of stellar variability and transient events. Modern sky surveys can monitor millions of stars simultaneously, detecting everything from subtle pulsations to dramatic explosions with unprecedented precision and temporal resolution. Gravitational wave astronomy has opened an entirely new window into stellar evolution, allowing direct detection of the mergers of neutron stars and black holes formed in the final stages of massive star evolution. These observations provide information about stellar physics that cannot be obtained through electromagnetic radiation alone, including constraints on the equation of state of nuclear matter and the formation rates of compact object binaries. The combination of gravitational wave and electromagnetic observations of neutron star mergers has confirmed that these events are responsible for producing significant quantities of heavy elements through rapid neutron capture processes. The detection of gravitational waves from merging neutron stars, followed by observations of the optical and infrared kilonova emission from newly synthesized heavy elements, represents a triumph of multi-messenger astronomy. Future space-based gravitational wave detectors will be sensitive to lower frequency gravitational waves produced by massive black hole binaries and extreme mass ratio in spirals, providing insights into the formation and growth of black holes across cosmic time. These observations will complement electromagnetic studies of active galactic nuclei and quasars, creating a more complete picture of how the most massive objects in the universe form and evolve. The search for gravitational waves from isolated neutron stars may reveal information about their interior structure and composition that cannot be obtained through any other means. Rapidly rotating neutron stars with small asymmetries could produce continuous gravitational wave emission detectable by current or future instruments, providing direct probes of matter under conditions more extreme than anything achievable on Earth. As our understanding of stellar physics continues to evolve, new questions arise about the fundamental processes governing stellar structure and evolution. The role of magnetic fields in stellar interiors, the details of convective mixing and transport processes, and the mechanisms driving stellar winds and mass loss all remain active areas of research with implications for understanding stellar life cycles and chemical evolution. Three-dimensional numerical simulations are beginning to reveal the complex dynamics of stellar interiors, showing that the traditional one-dimensional models used for decades may miss important physics related to rotation, magnetic fields, and convective overshoot. These simulations suggest that stars may be more dynamic and variable than previously thought, with implications for stellar ages, chemical yields, and evolutionary timescales. The discovery of thousands of exoplanets orbiting other stars has created new interest in understanding stellar properties and their effects on planetary systems. Stellar activity, chemical composition, and evolutionary status all influence the habitability of orbiting planets, making stellar astrophysics increasingly relevant to astrobiology and the search for life beyond Earth. As you continue your journey through sleep, let these stellar stories weave through your dreams like cosmic lullabies. The universe of stars extends far beyond what we have explored tonight, with countless more phenomena waiting to be discovered and understood. Each star in the night sky carries its own unique story of birth, evolution, and eventual transformation, contributing to the grand narrative of cosmic evolution that connects us all to the stellar furnaces burning in the darkness above. In the quiet moments before dawn, when Earth turns toward its nearest star, we witness one of nature's most reliable phenomena. Our sun rises each day with clockwork precision, a testament to the gravitational dance that has continued for billions of years. Yet this daily sunrise represents just one moment in a stellar story that spans unimaginable timescales, connecting us to cosmic processes that began long before our planet existed and will continue long after it fades away. The relationship between stars and time itself reveals one of the most profound mysteries in astrophysics. Stellar clocks tick at rates determined by nuclear fusion, with each star burning through its fuel supply according to its own internal schedule. The most massive stars race through their life cycles like cosmic sprinters, exhausting their nuclear reserves in mere millions of years. Meanwhile, the smallest red dwarfs burn so slowly and efficiently that they may outlast every other object in the universe, continuing to shine when the cosmos itself has grown cold and dark. This temporal diversity among stars creates a universe where different regions exist at different stages of stellar evolution simultaneously. In some parts of our galaxy, massive blue giants are being born in spectacular stellar nurseries, while in others, ancient white dwarfs represent the final gasps of stars that died before our solar system formed. The night sky becomes a time machine, showing us stellar evolution frozen at countless different moments across billions of years of cosmic history. Stellar populations tell the story of galactic evolution through their chemical fingerprints and spatial distributions. The oldest stars, found primarily in globular clusters and the galactic halo, are metal-poor relics from an era when the universe contained few elements heavier than hydrogen and helium. These ancient suns formed when galaxies were young and chaotic, before the orderly spiral structures we see today had time to develop. Their chemical signatures reveal a cosmos that was fundamentally different from the element-rich environment we inhabit now. Intermediate age stars like our Sun represent a middle generation, formed from gas that had been enriched by several cycles of stellar death and rebirth. The presence of heavier elements in their atmospheres tells of countless previous generations of stars that lived, died, and scattered their nuclear ashes into space. These metals, as astronomers call all elements heavier than hydrogen and helium, enabled the formation of rocky planets and the complex chemistry necessary for life as we know it. The youngest stars being born today inherit an even richer chemical legacy, forming from molecular clouds that contain the accumulated products of billions of years of stellar nucleosynthesis. These newborn suns will be able to create planetary systems with even greater chemical complexity, potentially harboring worlds where life might develop along pathways we cannot yet imagine. Each stellar generation builds upon the achievements of those that came before, creating an evolutionary ladder that leads from simple hydrogen clouds to the complex, life-bearing worlds we observe today. Binary star evolution adds layers of complexity to this already intricate story. When two stars form close together, their evolution becomes intimately intertwined through gravitational interactions and mass exchange. The more massive star evolves faster, potentially transferring material to its companion as it expands into a red giant. This mass transfer can rejuvenate the receiving star, giving it a new lease on life while hastening the demise of the donor. Some binary systems undergo common envelope evolution, where one star actually spirals inside the outer layers of its companion. This dramatic phase can either tear the system apart or bring the stellar cores so close together that they eventually merge. The resulting objects can be exotic stellar remnants unlike anything produced by single-star evolution, including blue straggler stars that appear younger than they should be, and peculiar white dwarfs with unusual compositions. The orbital dynamics of binary systems create natural laboratories for testing theories of stellar structure and evolution. Eclipsing binaries allow astronomers to measure stellar masses and radii directly, providing crucial benchmarks for theoretical models. The gravitational interactions between close companions can tidally distort stellar shapes, trigger enhanced magnetic activity, and synchronize rotation periods. These effects reveal how stars respond to external forces and help calibrate our understanding of stellar physics. Multiple star systems, where 3 or more stars orbit in complex hierarchical arrangements, demonstrate that our simple picture of isolated stellar evolution may be the exception rather than the rule. Many of the stars we see in the night sky are actually members of gravitationally bound groups. Their fates intertwined through gravitational interactions that can last for billions of years. The long-term stability of these systems depends on delicate dynamical balances that can be disrupted by stellar evolution, leading to ejections, mergers, or the formation of exotic objects. Stellar clusters provide natural experiments in stellar evolution, containing hundreds or thousands of stars that formed at essentially the same time from the same initial material. By studying the distribution of stellar types within a cluster, astronomers can trace how different mass stars evolve at different rates. The main sequence turn-off point, where the most evolved stars are just beginning to exhaust their core hydrogen, serves as a cosmic clock that reveals the cluster's age. Young clusters show hot blue main sequence stars alongside pre-main sequence objects, still contracting toward nuclear ignition. These stellar nurseries are often embedded within the molecular clouds where they formed, creating spectacular regions where star formation continues, alongside the early evolution of previously born stars. The Orion Nebula cluster exemplifies this active phase, where we can observe stars at every stage from initial collapse to main sequence burning. Old clusters tell different stories, with their original massive stars long since evolved into white dwarfs, neutron stars, or black holes. The surviving low-mass stars continue burning steadily, but their main sequence appears truncated compared to younger populations. These ancient stellar communities preserve information about conditions in the early galaxy, when star formation rates were higher and the chemical composition of the interstellar medium was fundamentally different. Globular clusters represent the most extreme examples of old stellar populations, containing stars that formed when our galaxy was still assembling from smaller fragments. These dense spherical collections of ancient suns orbit in the galactic halo, following elliptical paths that carry them far above and below the galactic plane. Their metal-poor compositions and extreme ages make them fossil remnants of galactic formation, preserving conditions from over 12 billion years ago. The study of stellar streams and tidal tails reveals how gravitational forces slowly tear apart star clusters over cosmic time. As clusters orbit through the galaxy, they experience tidal forces from the overall galactic gravitational field. Stars in the outer regions of clusters can be stripped away, forming extended streams that trace the cluster's orbital path. These stellar streams provide insights into both cluster evolution and the gravitational structure of our galaxy. Some disrupted clusters leave behind only their most tightly bound cores, creating objects that appear as dense concentrations of old stars. Others are completely dispersed, scattering their member stars throughout the galactic disk, where they become indistinguishable from the general stellar population. The fate of any particular cluster depends on its initial mass, orbital characteristics, and the specific gravitational environment it encounters during its lifetime. Stellar kinematics, The study of how stars move through space reveals the hidden dynamical history of our galaxy. Different stellar populations show distinct velocity distributions that reflect their formation conditions and subsequent evolution. The oldest stars move in highly elliptical orbits that carry them far from the galactic plane, while younger stars like our Sun follow more circular paths confined to the galactic disk. These kinematic signatures preserve information about galactic mergers and accretion events that occurred billions of years ago. When a smaller galaxy is torn apart by tidal forces and incorporated into a larger system, its stars retain memory of their original orbital motions. By studying the velocity patterns of stars throughout our galaxy, astronomers can reconstruct the accretion history that built the Milky Way from smaller components over cosmic time. The discovery of hypervelocity stars, objects moving so fast that they will eventually escape from our galaxy entirely, has revealed new aspects of stellar dynamics and galactic structure. These runaway stars may have been accelerated by encounters with the supermassive black hole at our galaxy's center, by supernova explosions in binary systems, or by gravitational slingshot effects in dense stellar environments. Their extreme velocities carry them on trajectories that will take them into intergalactic space, making them among the loneliest objects in the universe. Stellar archaeology uses the chemical compositions of individual stars to trace the history of element production and mixing in our galaxy. Each star preserves in its atmosphere a record of the interstellar medium from which it formed, carrying information about the supernova, stellar winds, and other processes that enriched its birth cloud with heavy elements. By analyzing stellar spectra in detail, astronomers can reconstruct the chemical evolution of different galactic regions over billions of years. And so our cosmic journey through the stellar realm draws to a gentle close. We've wandered among stellar nurseries where new suns are born, traced the ancient light that connects us to distant worlds, and discovered that we are truly children of the stars themselves. Each breath you take contains oxygen forged in stellar cores. Each heartbeat carries iron created in supernova explosions. As you drift into peaceful sleep tonight, remember that you carry within you the very essence of the cosmos, temporary stardust that has learned to dream and wonder about its celestial origins.